I have to ask again if everybody agrees with the recording of this session.
Yeah.
Yes,
Yes, I agree.
Okay, if everybody agrees, now we can start this session. And first of all, I have to say thank you for the participation of you all in some adverse conditions, but I think everything will be okay. When Daniele starts to talk, I will ask for everybody to turn off the sound so we can hear better. We avoid interferences. Daniele will have up to 60 minutes to do her presentation. After that, we'll start to argue the candidate, okay? So Daniele, are you ready?
Yes, I am.
Okay, so please start your presentation.
Okay, thank you.
And good luck.
Oh, thank you. Thanks to everybody that's watching this presentation. Thanks to the evaluation committee and my advisor and the staff that arranged everything for this defense happens. My name is Daniele and I will present my thesis, whose title is The Use of Giant Gaussian Process Model to Study the Paleomagnetic Field of the Kiaman superchron. During this presentation, I will talk about some introduction and some theoretical background, and after I will present the main results of my thesis. The first main result is about the chapter 3, that is about the paleomagnetic results from Mafra formation. After, I will present a directional outlook to the giant Gaussian process model of the geomagnetic paleocircular variation, that is the chapter 4. After, I will present the results from chapter 5, that is about properties of the geomagnetic field during the Kiaman superchron. And after, I will present the main conclusions of these theses. So, my main intention during these 5 years was studying the geomagnetic field from the past. And when we look back to the properties of the geomagnetic field, we can discover the evolution of deep Earth. However, as we go back in time, the remaining record of the paleomagnetic field in rock becomes more scarce in time and in space. Thus, a simplified model is used to study the geomagnetic properties. The simplest mode of a magnetic source is a magnetic dipole, and the fundamental hypothesis of the paleomagnetism is that the mean field along thousands of years is compatible to a field generated by a dipole centrated and aligned to the rotation axis of the Earth. So with this main hypothesis, we can discover the past configuration of old blocks of continental blocks. As we have the inclination of the magnetization of these rocks, we can find the latitudes where these blocks were in the past. So a set of different stands of the geomagnetic field will be around the mean field, that is the time averaged field, that is compatible to gauge field. And these changes, these variations, we call by paleocircular variation. And changes in the paleocircular variation, if the paleocircular variation is more grouped or more sparse, it can reveal differences and the history of the operation of the geodynamo caused by different scenarios of deep Earth in the geological scale of time. This sequence of data that reviews instances of the geomagnetic field in the past can be a sequence of sedimentary rocks or a record, paleomagnetic record from a sequence of lava flows. the best rocks for studying paleosecular variation are the extrusive igneous rocks that are considered as a spot reading of an instance of the past geomagnetic field, because of the cooling of this type of rock is fast. The PSV statistical model type that I studied during my PhD was the giant Gaussian process models. These models are able to predict at any place on the Earth's surface distribution of directions of the magnetic field. These models are based on the description of the field in spherical harmonical functions. So the magnetic potential for a magnetic internal source can be described by spherical harmonical functions in r, theta, and phi, where r is the distance from the center of Earth, theta is the polarity, then phi is the longitude. And these scalars here are called by the Gaussian coefficients that are the GLM and HLM from of L and M degree. And the magnetic field is the gradient of this magnetic potential. So the idea of the giant Gaussian process model is that these Gaussian coefficients vary along the time following a Gaussian distribution, having a mean value and standard deviation. So here we have the GLM Gaussian parameters varying with a sigma LM standard deviation, and here HLM varying with sigma LM standard deviation. So each instance of the geomagnetic field in the past will be a combination of a list of random sampling of these coefficients. As each one of the components of the magnetic field is a linear combination from these Gaussian coefficients, so each one of these magnetic components will follow a Gaussian distribution. So for the magnetic field, we have the magnetic field given by a giant Gaussian process model will follow 3D Gaussian probability density function that here is indicated by G of B, where lambda is the inverse of the covariance of matrix of B, and M here is the mean field. The mean field is described by the mean values of, Gaussian coefficient from the mean, the TAF, the time averaged field. The thing is that I work with directional data, so from paleomagnetic data sheets. So I don't need, these data don't have the intensity value. So I needed to know the probability density function without the intensity, only look into the directional distribution. And for doing that, we needed to remove the intensity of B. So we needed to integrate along whole this probability density function for having this S of U that I will call by S until the end of this presentation. That is the directional probability density functions for unit vectors, and this unit vectors is the unit vector for the magnetic field. So here, one exercise is showing some random samples from the CP88 model. That was the first GGP model proposed. It was proposed by Constable and Parker, and they proposed the idea from giant Gaussian process model process happening for explain this long scale time time of variation of the field. And here we have some synthetic samples that I drawn from CP88, and the iso-value curves of the S of U of CP88, just for comparison here, and just to watch how the distribution, and this distribution is rotated to the vertical. So the center of this projection is given by the time averaged field, the expected direction from the time averaged field. So it's easy to see better the distribution of directions, and we are going to use this kind of projection till the end of this presentation. So that's why I'm explaining now. And we can see that for distributions near the equator, we have a more dispersed distribution and more elongated. And when we go up to the poles, this distribution becomes more tight and more circular. All available GGP models that we have are related to the last 5 million years, to explain the field of the last 5 million years. The last one was the TK03, that is a simplified giant Gaussian process model. It is simplified because it needs just only 3 parameters to define it, and it means time is a gauge model. The mean field is only the gauge model, so the only Gaussian coefficient that is different from 0 is the G10. And for determining this model, we need just the mean value of G10, alpha parameter that is proportional to each one of the Gaussian standard deviation of each Gaussian coefficient, sigma Lm. So following the equation proposed by Constable and Parker when they proposed the idea of the giant Gaussian process. And the great difference of this model is the insertion of this beta parameter, which will multiply these standard deviations for the antisymmetric family's coefficient. So even with this simplification, with only 3 parameters compared to the last the previous models that were fitted, actually had the standard deviation, each one fitted up to the degree L until up to 2. So for the other models, more than 5 parameters were needed to explain the model. Even with this simplification, only 3 parameters, the sigma Lm, the standard deviation of TK03, follow the same tendency of the other sigma Lm from the other model, being more important for lower degree and less important for higher degree. The TK03 was fitted to the MM97 database, the last 5 million years of polysecular variation from lavas. And here I have a plot at latitude 0, 30, and 60 from MM97 database. These are directions rotated to the vertical as the way that I explained already. And here we have the predictions, some synthetic samples from TK03, and we see that they are similar. They represent well what we see in the real data from MM97. And here we have the VGP calculated from these synthetic samples. And what we see is that the scatter of the VGP starts for lower values to upper values going to the poles. So here we have the prediction from TK03 compared to the data from MM97. And this model, TK03, is the best model that explains the latitudinal variation of MM97. And this Tauxi-Kent were the first that proposed the variation of elongation, that is how these distributions are elongated along north and south direction, how these elongations vary with latitude. And with the proposal of this model, they also proposed a method for correction of inclination shallowing bias in sedimentary rocks. So if you have sedimentary sequence that suffered of inclination shallowing bias, the observed inclination will be lower than the real inclination from the field. And this flattening factor will be different from zero, will be less than zero. And according to Tauxi-Kent, the distribution of direction should follow a shape, so should follow elongation. And if the sedimentary sequence suffer of inclination shallow, this distribution will be squeezed. So we apply different flattening factors until we find the flattening factor that corrects the distribution from the sedimentary sequences that is compatible with the TK03 model. So after that, we have two methods for correction of inclination shallowing process. We have the first method that is based on the remanent anisotropy, that is from Jackson, 1991. And after we have that it is from, you do the measurement, the remanent anisotropy, you do the measurement from the GCD, the flattening factor from the rock that you are studying. And the other method is about the shape of the distribution expected for the paleomagnetic data. Inclination shallowing detection and correction is a mandatory procedure for sedimentary rocks. I have been working with sedimentary rocks since I was undergrad, and I was studying Permo-Carboniferous rocks from Ghana, Africa, and after I did my master with the sedimentary rocks from San Francisco Basin. And in 2009, when I published the San Francisco Basin, I used the EI method for correcting my data. But I used this method without knowing if the Kiaman superchron, because these data from San Francisco Basin, they are from Permo-Carboniferous rocks that inserted in the Kiaman, and I didn't know if the Kiaman's superchron had the same directional distribution from the last 5 million years. That was a prediction from TK03. And other studies used this EI method, and we had no idea if this is a thing that we should do if the field is the field of superchron like a Kiaman have the same shape. We don't know. We didn't know the distribution, directional distribution from the Kiaman, but what we already know about the superchron Kiaman is about the VGP dispersion. And when we look into the VGP dispersion, the variation, the latitudinal variation with VGP dispersion, we see that it is too similar to what we expect from superchron, but it's different from the last 5 million years. So here we have a modeling that was done by Oliveira and others in 2018 with sedimentary data and with igneous data from Kiaman superchron. And we see that the results of Oliveira is too compatible. This is the red model is from Oliveira, and the results of them is too similar from the results of the Cretaceous normal superchron from Begin and others. And it's different from the 5 million years model from Johnson and others. And the great difference we see here in the small contributions of symmetric components for those models. So we know that in terms of VGP, a superchron is different from what we have for the last few million years. But we don't know, maybe we have a small dispersion, but we can have, maybe we have the same elongation, and so that's why I follow some questions along my PhD, the development of my PhD, and my main results that I will present to you is related to these questions. So are the distributions of directions from the Kiaman superchron similar to recent fields? How are the directional distributions drawn from other versions of GGP models? What is the best measurement to evaluating for evaluating a distribution of directions with scatter, elongation, precision, or others that I will present? Can the paleosecular variation during Kiaman be described by a GGP model? So I will first present the main results of chapter 3. This chapter presents new and detailed paleomagnetic results from a sedimentary section from Mafra formation of about 300 million years. Is inserted in the Kiaman superchron, is the middle portion of Itararé group, that is the Permo-Carboniferous glaciation of the Paraná Basin. And this is the sampling section that is nearby Mafra City in the Santa Catarina state, which is in the southern part of Brazil, in the east border of the Paraná Basin. We also sampled, we sampled detailed in the first 3 meters here for doing cyclostratigraphic analysis. And the cyclostratigraphic analysis were done by the cyclostratigraphic team that is led by Daniele Franco from Observatório Nacional. And the analysis of them indicates that 800,000 of years is the time of deposition of the complete section here of 5 meters. The demagnetization, the best data for analyzing from the demagnetization are the thermal demagnetization, where I could discriminate well the secondary and the characteristic components. The characteristic components were determined for temperatures above 400 Celsius degrees. And here I have a plot from Ernesto and others that we have more plots of intensity of demagnetization, thermal demagnetization. Of other samples are distributed along the section. We have more data, but this I think is sufficient enough to show that the main behavior of the characteristic component is that the characteristic component is removed before 580 degrees. That is the highest temperature of unblocking from magnetite. So we conclude that the main carrier for the characteristic component of Mafra rocks are the magnetite. We also see the vertebrate transition in low temperature curves. So because of the shape of direction of distribution of direction of Mafra, that give me other things to work on, and because of this distribution, I was not able to apply the EI method and compare to the remanence method for inclination shallowing correction. And I will show to you in the next slide. So using remanent anisotropy, I found a flattening factor of 0.97, that it means almost nothing, no correction, as we see that the flattening factor is the ratio between the observed inclination and the field inclination. And the final paleomagnetic pole for Mafra, that is this star here. Here we have two stars, if you can observe, but if you cannot, you can believe that we have here two stars, and they are the correct and uncorrected final paleomagnetic pole using the flattening factor. And we can see from this plot that the age of the poles are are differentiated by this pattern of colors. So we see that the position of the paleomagnetic pole from Mafra is compatible with ages with other poles of the same age for South American plate. And that are the 19 and 18 that is positioned here is from rocks from Chile. And also we see that the final paleomagnetic pole from Mafra is in agreement with older ages than the triangle here, that is the Rio do Sul paleomagnetic pole, that is a formation from the Tararé group, but is the top of the Tararé group, and Mafra is the middle, so it's younger than the Mafra. So it's a result that confirms the compatibility of them. So here we have the discussion about the distribution of Mafra that I told you. So here we have the distribution of directions per size of Mafra sedimentary sequence. And what I put here some synthetic samples that I drawn from TKO3 and other versions of this model to try if I could find a model that best fits with the shape and the dispersion from Mafra data. And we see that these are for the same latitude, and we see that the data from Mafra formation is totally different from what is predicted by TKO3. And also here we have the better way of looking to this is the elongation graphic, and here we have the VGP dispersion. So in this dashed line here is the prediction of the scatter of VGP from TKO3, and here we have the Mafra result, and we see that it is totally incompatible. And here we have the elongation from TKO3, and we have the other versions that I have here that I changed the model of TKO3 to try other situations, other type of models that could fit for Mafra data. I also plot here the two longest sections of igneous rocks, that is Bacali Formation and Oslo Graben, and they have the same, they have a small VGP scatter like Mafra, but in terms of elongation, they are not agreeing each other, And also we have a big, long, great limits of
Daniele, acho que desligou o seu som.
Vocês estão me ouvindo?
Yes.
Sim, yes.
Yeah.
Okay. So in terms of elongation and shape of direction for Kiaman, we cannot have a strong conclusion from that. But what we can say is that the VGP scatter is totally different, and from the models that have this size of dispersion, we should observe higher values of elongation in the prediction. So, what's doing? So the main conclusions of this chapter is that the paleomagnetic results from map formation are the largest known section of primary sedimentary data from Kiaman times with anisotropy inclination shallowing correction. The new paleomagnetic pole is compatible with what is expected for the South American plates for the time. GGP model with reduced dispersion will produce greater elongations mainly in the equator. And this new result is an alert that the indiscriminate use of EI method may be inaccurate for any period over which the method has not been tested. Now, the main results of chapter 4. In this chapter, I propose a new way of characterizing the paleocircular variation from distributions of direction. So I needed a way of measuring the distribution not only with the elongation, because the elongation gives us only how the distributions are elongated, but not how they are spread or they are grouped. And I learned from the models that we know that this distribution can be more spread or more elongated. And in this case, we can have in the Mafra case, we can have a distribution that is more grouped, but also elongated. So I needed to have a number, a value that I would measure these distributions, and I needed to be able to predict theoretically for modeling purpose this value. So if I look at the declination, for example, if I look at these are all rotated to the vertical distribution. And if I look at for the variation of the declination, for example, I would look to this distribution that is too small and have a big variation in declination. So this value would not have the meaning that I want. And I know that if I look at distribution of data, and if I want to know how wide this distribution is, I know that I will look to the standard deviation, the variance of this data. So, and when I want to look to a distribution and decide if it is spread or it is elongated and talks about how the distribution is, I need, in terms of directions without intensity, I use the equal area projection. So for measuring the shape and the scale of a distribution of directions, I use the standard deviation of equal area projections of distributions rotated to the vertical. And I was able also to predict this because I knew that the distribution, the probability density function for directional data. So I was able to predict it theoretically and experimentally. So here, for the data set for calculating how the distribution is elongated in east-west direction, I would use the standard deviation E, that I call standard deviation E, that is the component, the coordinate XE, and I would see the standard deviation along north and south. I would measure how the distribution is spread at along north-south direction. So I'm able to do this experimentally with rotated distribution and also theoretically. So the test that I will show now is doing exercise of generating 10,000 of random samples from a GGP model and comparing to the theoretical values of mean values XE. So the mean value of XE at the position in this X of the mean value, and the mean value of XN, that is the mean position in this direction, and the standard deviation. So the first result is about the mean value. And here I plotted, in the same plot, the mean value of XE in dashed purple line. And here the stars are the results from the simulation, 10,000 of synthetic simulations. They are compatible and plots around the value. And here we have the purple curve is the mean XN, so along the north and south, the mean value. And and this value is different from 0, which means that the mean value is different from the expected direction from gadgets. And this is a bias that we expected. It was already discussed by other authors, that when we work with the unity vectors for doing mean determinations, we have these effects. So here we have the same plot, but using inclination. So we have a delta inclination for latitude. Oh, I'm sorry, I didn't say that it's the latitude, and here we have the equator and the pole. So we have a bias that is the greatest values of delta inclination is near latitudes of 20 something for north, for south, and here in north and here. And when we take this the simulations of directions and calculate VGPs, we have the mean pole. That is also, we have a different, this is the latitude of the pole. So the pole is not positioned at the 90th degree, that is the geographic pole. So we have a bias here of 1 degree. And when we calculate the expected direction from this final pole, we diminish this bias. So it's a good thing to do instead of doing the mean of the directions, do the calculation of the expected direction from the mean pole. And when we use a cutoff of 45 degrees, we diminish more the delta inclination. And when we apply a iterative cutoff, like the Van Damme cutoff, we remove for complete this effect of this bias in inclination. So here are the plots of sigma A and sigma N. So the sigma E, that is the east and west, is here in dashed line, and the stars for simulations. And the sigma N is the purple line, purple curve here, and the circles that are the projections from simulations. They are compatible. They plot around the theoretical value. And the good thing that we see here is that it is symmetric with the equator. So, so for using this kind of measurement for old rock that we don't know the hemisphere or we don't know the polarity, doesn't matter because we have symmetry here to the equator, symmetry. And here we have, if you want to know how is the elongation, we have the elongation E prime, that is the ratio between the standard deviation and E square, that is about the same elongation of Tauxin and Kent, but in this case, we can predict theoretically this value. So our E prime here is this curve. And also, if you want to see how dispersed is this data, you can watch the variability of them. So you multiply sigma A and sigma E, and you have the variability of the distribution. So our proposal to measure the size of the distribution and the shape is looking to these standard deviation sigma E and sigma N. And I tried from simulations compared to theoretical values, and I got good results. And now I try real data. So I take the PSV10 database from Cornellio 2018 to see if the recent model, recent records of the paleomagnetic field would be compatible what we expected from using these measurements, and if these measurements are diagnostic for determining PSV model. So we see that the data from PSV10, this is in blue, we have the mean XE that is around 0, so it's compatible with what is expected from gas. And we see that for XN values, that it is this red circle, that they have values that is for positive values that is similar what we expected from a gauge model, a gauge mean field. And here we have the standard deviation predicted by TKO3, that is this red and more strong red here, dark red, and here we have in red circles we have the data that seems going for sigma N, that seems to diminish from the equator to the pole, and are greater than sigma E. The standard deviation is S, showing that the distribution of these directions are elongated. And we have these different data that's totally different what we are predicting here. But in this case, we have the data that is separated in this beam of latitude is almost all from McMurdo region. That is a sequence of data that has a different behavior, and also we see anomalous values of intensity in this region. So maybe this is only a local field that is the sampling is showing more because it is the majority of data of this beam of latitude. And also, we present here the BCE model, the BCE 19, that is this red line here and this blue dashed line. That is the model that best fits to the PSV 10 data. So in this chapter, we also present what would happen if we had a GGP model different, simplified, but different with different values of alpha and beta values. So we see that if you change the alpha parameter, we increase the sigma E and sigma N at the same way. And when we change beta, we have different latitudinal variation from the other exercise. So the partial conclusions from the chapter 4 is that we have presented a new type of PSV statistic based on the shape and directional PDF. On the shape and scale of directional PDF given by a simplified GGP model. The PSV parameters are the standard deviation sigma E and sigma E. Our results clearly indicated that the best way of determining a paleomagnetic pole is using the iterative cutoff procedure. For a zonal GGP model with GAD mean, the latitudinal dependence of sigma E and sigma N is symmetric, and this is good for using for old data. And the latitudinal variation of sigma E and sigma N seems to be diagnostic and can be used for further modeling. Now I will present the last chapter of results. In this chapter, I explored the available Kiaman data from literature. I found the majority of poles of studies in the Global Paleomagnetic Database, MAGIC and PINT database, and using the bibliographic search. Here are the maps with the position of the studies, the area of studies. And during this compilation, I used a not so strict filtering when compared to other studies, but I have the intention of having the great number of directional data as possible. So the criteria used was paleomagnetic poles from igneous rocks, primary magnetization, age inserted in the Kiaman superchron, the samples with the MAGIC code at least 2, exclusion of sedimentary sites, exclusion of unreliable sites, only data sets with at least 5 igneous sites, and the evaluation of whether the data set distribution sampled the geomagnetic PSV using the Dinin method that defines alpha 95 minimum and maximum depending on the number of the sites. The problem here is that we change the limit using the own database because we think that Kiaman paleomagnetic field is different from the whole history of the Earth. So because of that, we fitted using the same procedure as the new limits for the Kiaman data. The data sets were merged and for using beams of paleolatitude, but for doing that, I didn't use a predetermined reconstruction for doing that because first I need to find a Pangea that I want to use, or Pangea B or Pangea A. But this is not the biggest problem. The problem is that when we don't know the exact age, the exact time of formation, we can use a configuration of paleocontinents that is not compatible with the age. So we would put more error in this procedure. So I decided to use the expected direction for each data set. And for calculating the expected direction, I used the mean paleomagnetic pole using iterative cut of Van Damme, as I told you in the last chapter, is the best way of doing that. And with the expected direction, I rotated the direction to the vertical. So I did this, for example, here for data between 30 and 40 degrees. I got all data sets that has paleolatitudes, that is compass, the expected direction has paleolatitudes between 30 and 40 and put all together to represent the behavior of Kiaman along this band of latitude. Then I did this for all latitudes. So we have latitude bands of 10 degrees. And here we have all database of Kiaman plotted here. And we can already observe here that the data from the equator equatorial latitudes are more elongated and more spread, and after we see that the distribution becomes more circular. And we can watch this better, look into the results of standard deviation E and N. And here I plotted the TK03 model for the last 5 million years, the BCA model that I proposed in the last chapter, and to compare with the data of we found for each beam of latitudes of Kiaman. Here in purple circles are the sigma n, and the stars are sigma e. And we see that all data are for lower values of standard deviation. We also see that for latitudes higher than 10 degrees, we have almost circular distribution. The sigma e is too similar to sigma n. And the only latitude that we have a statistically difference between sigma n and sigma e is the equatorial latitude. So so it's a behavior that is totally different from the last 5 million years. And the only latitude band that has compatible values with the 10 million years model is the equatorial. And here we should observe that this determination is not taking care with the experimental error that is considered for each site mean. So each site mean has an alpha 95, and these have an experimental error associated. So if we have a way of removing this error, to know exactly this error and to have only the distribution associated to the field, we can imagine that the paleosecular variation from Kiaman is lower than this. So I try other types of filtering to see if this anomalous behavior would change. So I try cut off number of sites higher. I try 5, 10, 20. And also I try other kinds of filtering process that we see in databases, in other databases that is more restricted. And I didn't see too many differences here. And what I saw that we can see easily here is that the limits of confidence increased when we take out the data, and also that some latitude bands lost were complete the data, the results. So with this result for extrusive rocks from the database of Kiaman, I try to find a GGP model that explains this anomalous behavior. And this is the minimum model that I found for sigma n and sigma e. And we see that there is a systematic difference between the data and the model. So the model is around the data, but is not totally fitted to the data. So what we can conclude from this is that maybe the geomagnetic field from Kiaman times is not explained by a simplified GGP model, or that this is just an effect caused by the unremoved error that we have in this database because of the experimental error. So I try some simulations, trying different types of experimental error that we can find in databases. So what would happen with a model like one of the Kiaman model? What changes an experimental error would do with the result? And for a model like Kiaman and a model like BCE19, and we see that when we put experimental error, we change more significantly when we have a small PSV, that is something that is expected. And also we see that the elongation becomes more circular than when we apply the same time of error to fields that is more energetic, like the last 10 million years. So the main conclusions of this chapter is that we presented the Kiaman igneous database that is the most complete list of site directions from Kiaman period. The directional Kiaman PSV results are approximately circular, concentrate, and essentially invariant for latitudes higher than 10 degrees, which is completely different from what is predicted by recent GGP models. As the experimental error were not considered, this small PSV behavior can be still more reduced. So for finishing this presentation, I will resume the main conclusions of my work. The Mafra paleomagnetic pole presented in chapter 3 is compatible with results from South American plates of the same age. Iterative cutoff is the best way for determining a paleo inclination or a paleomagnetic pole. A new type of PSV statistic is presented in chapter 4, the sigma E and sigma N. The Kiaman database is the most complete list of directions per site for this superchron, and it reveals a small directional PSV variation. The Kiaman geomagnetic field can be much less variable than its PSV result. And therefore, if the intention is to study this minimum long-scale variation of this period, future work will need more accurate experimental procedures. Eu gostaria de agradecer a todos que estiveram comigo em toda essa jornada, a Universidade de São Paulo pela infraestrutura incrível e pelo pessoal também, né, pelos recursos humanos e infraestrutura, que é sensacional, ao governo federal, que me apoiou durante meu estágio fora, no SCRI, a minha orientadora, que sempre me deu o meu tempo, me respeitou minhas ideias, e foi comigo aí nessa longa jornada de pesquisa, os pesquisadores, colaboradores no meu projeto, os funcionários, professores, estudantes do IAG e do SCRI, meus amigos e minha família, que eu amo muito, por todo o apoio. Hey.
Thank you, Daniele. Before we go to the second part of this of the session, I'm wondering if anyone needs a break for a coffee, water, or anything else. I think it's better if everybody now turn on the sound so we can talk and I can hear the answers. Okay, Daniele will stop the presentation.
So Marcia, it's up to you guys.
Okay.
Okay, so can we move to the second part or you need a time? Daniele, are you okay? No sound, Daniele, turn on your sound.
Okay.
Okay, so let's start with the comments, the question. So I will ask to Kathy Constable to start with her questions and considerations. And I take this time to thank you very much for your participation, involvement with this project, and accepting Daniele for his for the period he spent at your laboratory with your group. Okay, so please.
So I'd like to thank you and Daniele for coming to visit us at Scripps. It's been a very enlightening experience, and I want to thank Daniele for a very nice presentation of her work, which I enjoyed a lot. Of course, I've got a couple of questions, and these are really more about what might be done in the future than anything that that covers what you talked about. Let me start with the MAFRA work. And one of the questions that I think might be very interesting there would be if it were possible to understand what the impact of the sedimentary smoothing is on the paleosecular variation that you measure, and whether that has any impact on firstly on the elongation results, and secondly on whether it affects the overall size of the paleosecular variation that you're able to measure there.
Yeah, the size of paleosecular variation, you can say that yeah, it is smoothed because of the time of duration of each one of the sample that I measured. I should try an explication not only for the group direction, but for the elongated distribution. Maybe when we smooth this time, we are eliminating components that vary differently. So in a but I really don't know how to explain this, but this is a good question to think. But at the same time, when we look to data from last few million years from larvae, we see that the field is not so equal and the same in all places.
Mm-hmm.
So the elongation maybe is a local effect of the variation of the field, but we should also see if this smoothing process is eliminating systematically components of the field that is related to the variance of east and west of the magnetic field. So this is a good question. I don't know how to answer.
Yeah, maybe it's one that could be addressed perhaps by looking at long sedimentary records in other localities, if there are any, which is a question I certainly don't know the answer to.
Mm-hmm.
Okay, so my next question is about really the question of how we could improve these GGP models, or do we need to do something different in the future? Because when you look at the comparison with the PSV10 database, there is this discrepancy at high latitudes between the BCE model and also with TK03. And is that something that, and we've already between ourselves discussed the idea that this might be associated with low paleo intensity values that you see at in that high latitude region in the southern hemisphere. So I think the question is, if we were to look at something where we had a different time averaged field model, would that make the GGP model work for that time interval? And then the question is, how much does that matter for going back to the Kiaman, when maybe you have, what values of intensity do we know? What do we know about intensity in the Kiaman? Two questions in there.
I got the first question, but I didn't got about the intensity of Kiaman. I didn't.
Okay, why don't you answer the first one first, and then we'll go on to the Kiaman.
Yeah. So about the changes in the simplified model of GGP, I think we are able to do that for PSV10 for data that we know, the longitude, the position, and the hemisphere, we know this. And we could try other task models and other persistence components of field. We could try different variation in terms of standard deviation from the Gaussian coefficient to try this, like the TJ98, that is the non-zonal field. We could try this also. So for this kind of data, I think we can improve too much better. But when we want to have a measurement, the measurement that we present here for the PSV10 is like the overall behavior for the last 5 million years. We use like the mean color of a rainbow, you know. So how this mean color is different from other geological times. So it's kind of a measurement how the geodynamo was working for a long scale of time, looking from with a distance, you know, without so detailed. So first, for the last 10 million years, I think it's possible to change the GGP model, or we think about other models. But for doing this comparison, I think we need to know that we are not able to look to a sequence of the past and say, oh, this is not compatible with the GGP model that I have for Kiaman, so it's wrong. No, it's about an overall behavior of the geomagnetic field. So like this is not, I don't know. So I think we can change for the last 10 million years. We can put everything you want. Or thinking about other behavior, I don't know. We need to think about this. And for old geological past time, we need to use a simplified model.
Yeah, so I think the other question I have about the distant past is whether there's anything that we could use from the field strength during the Kiaman that would allow us to get more insight into what's going on there.
Yeah, I take the paleointensity from the pinch database from Kiaman, and it shows higher values of intensities during the Kiaman, I think. Yeah, because I was trying to change the intensity along the GGP model that I was testing in the beginning of my work. But I used the intensity from TK03 because as it is proportional to the standard deviation, so doesn't matter in this way. And I was only looking to the direction of variation. So I need to think about maybe changing, put some persistent field during this period using paleointensity results. We need to see this. I don't know.
Yeah. Okay.
Thank you.
Okay, those are my questions.
Thank you.
You're muted.
Me? No.
No, Marcia.
Marcia.
I forgot. Okay, thank you. Thank you, Kathy. Augusto, could you please make your questions and considerations? Thanks.
Okay. Hello to everybody. Nice to see you, all of you.
Hi,
Nice to see you too.
Ricardo. Hello, Daniele. Nice to meet you.
Nice to see you.
Hello, Daniele. Okay. My consideration about the thesis, first of all, then I have a couple of comments and questions, but I like it very much. I really like it very much, this thesis. I like it reading it. I have only had contact with this thesis on your paper on JGR. That was the only thing I knew about it when it came. And I found a thesis that is very much coherent, and which is not just 3 papers attached and see how we make a sense of all of that. I mean, it's just a thesis with objectives, very clear objectives, and very clearly explain how you deal with that, and then presenting your results. And of course, as any good thesis should have, at the end you have more questions than you have at the beginning. But that's the way it should work. I mean, if not, I would be very suspicious about a thesis that only give answers. Yeah. So my congratulations. I also like very much how it is written.
Oh, thank you.
I am used lately to see so many typing and writing errors in theses that sometimes I am afraid when I go into a thesis. And this was really very, very nicely written and very nicely presented. So my congratulations to you for that, and of course for your supervisor too. And so I'll go for a few comments, no? And I wrote them here just to have it better explained. One of the things that caught my attention was the low accumulation rates that you infer from the cyclostratigraphy of Mafra formation. It is something like 6 meters per million year. Which, okay, it could go. But when you look at the whole stratigraphy of the Mafra formation, according to what is published, you get that the rhythmites only may reach up to 70 meters, 6 or 70 meters. So you will have 10 million years just recording is 60 or 70 meters only on the rhythmites of the Mafra formation. And then Mafra is just not 70 meters, it's 200 meters thick. Of course, not rhythmites, other phases, which may be faster for the position. But then on top of that, you have the Rio do Sul formation with around 100 meters more rhythmites. And this will make the Itararé subgroup of several tens of millions of years. I mean, if can you accommodate these low accumulation rates in the whole of the stratigraphy of the Paraná Basin, or you go just out of scale? That's something I want to ask. Probably also Daniele can say something about that, or Marcia, or whoever knows much better than me the stratigraphy of the whole Paraná Basin. But it looked to me as something peculiar, because the Paraná Basin has a very, very thick sedimentation, and so there is no problem at all with those 10 million years just for the rhythmites of the Mafra formation.
I really don't know how to answer this question, but the thing that I know is that the deposition is not the same. So we are in a glacial system, so we have two variable sedimentary rates. And I think, I really don't know how to answer your question, but it's important to know this. I don't know.
Okay. No, it's just something that, I mean, perhaps it's just a suspicion or something going wrong there, but perhaps it's nothing going wrong there. So it's
maybe I can add something.
Sure. Yeah,
Excuse me. This sedimentation is in a closed environment, like a lake. So if you look to the stratigraphic column, you see that Mafra, Rio do Sul, and also Itu, rhythmites to the north, they are local sedimentation environments, and being of glacial origin, they really have a higher sedimentation rate. Maybe this needs some reevaluation. Daniele can comment about this, about cyclostratigraphy, but we are basing these conclusions on what you have from Mafra, Rio do Sul, and also Itu. Now, Daniele, I think you can comment this later. Okay. But this is local. This is not spread over the basin, so okay. we can fit inside the stratigraphic column.
Okay.
Well, I don't know if I got everything, but particularly in the case of Mafra's Olsen quarry succession, we found by cyclostratigraphic analysis, after removing the linear trend, we found very clear spectral peak ratios, which obeyed the Milankovitch signals, which as predicted for late Permian times. And by examining the distribution of data, we can recognize the succession of short eccentricity cycles, which allow us to estimate, together with another little shorter but orbital cycles as well. The succession has something like 50.4 kilo years. But the cyclostratigraphic signals, together with evolutionary harmonic analysis, we can see the trend of these signals throughout this succession, how they evolve, even with changes in sedimentary rates we can recognize it. All of it are there.
Okay.
Pretty clear.
Okay. Thank you, Daniel. Okay. A second concern I have is in your last chapter, chapter 5. They using data from intrusions, no, from intrusive bodies in your analysis. I know that dikes are probably okay.
I use the
No, as far as they are not too thick. And then you show that if you exclude the intrusive bodies, then nothing changed too much. So
yeah.
But anyway, I mean, I have some concern of using all intrusive rocks as if were the same, and I wouldn't use plutons at all. I just discard plutons because they may take 1 million years to cool, I mean, or more. But it's not the same with dikes. And dikes, mainly if they are narrow dikes, thin dikes, perhaps 1 meter thick or 2 meters or something like that, they're not so much different than lavas. So perhaps you could have a larger data set than only with lavas, but excluding plutons or pegmatites or that kind of rocks. So that's probably a kind of recommendation to look at that. Some dikes are very, very thick. If you get a dike that is 50 meters thick, well, that probably took a long time to cool, but some thin dikes might not. So I would suggest that. The other thing is just, it's not a concern about your thesis, it's just a question. And since Katy and Marcia are here, and Ricardo too, perhaps Daniele and then can tell me that if I am wrong in what I am thinking about. I mean, I was completely convinced in your analysis about what you found paleosecular variation during the Kiaman period, the superchron. I am convinced. The data you show, the analysis you made. But I wonder how much of the results might be biased because all data necessarily comes from Pangaea, which was virtually already assembled by the early Permian. Yeah, and if you see the reconstruction of Pangaea, it was occupying more or less a north-south distribution in the Earth, but only covering something like 120 degrees longitudinally. So you have only 1/3 of the Earth covered.
Yeah.
All data come from 1/3 of the Earth.
Yeah.
You can't do nothing about that because there is no way of getting result from the other 2/3. But
yeah.
could it be possible? Could it be possible to test if similar results to what you got in the Kiaman can be obtained if you analyze younger rocks and just select rocks in, let's say, longitudinal bands, like say 1/3 of the Earth, another 1/3 of the Earth, and another 1/3 of the Earth, and see if you get something that resembles the Kiaman results?
Yeah.
I don't know if that is maybe possible or not.
Yeah.
It's just,
yeah, we are in only one side of the.
Yeah, 1/3.
Yeah. Yeah, this is possible to do, to see if there is a systematic difference between one side of the Earth. Yeah, it's possible to do with the last few million years data. It's possible. And this is a good question to try, because if it is true, we are only sampling in a long time scale, only one side of the main behavior of the field. So
yeah, could it be possible to try something like that with the Cretaceous normal superchron?
You should
not enough data, but
yeah, you should have a good reconstruction.
Yeah.
Good data, good aging.
Yeah.
Because you need to put in the
Yeah.
reconstruction to find the longitude for that. But I think it's possible because it's not so. If you're going only to separate for long scale of longitude, you're not going to do too much error in this. And you use the paleo inclination for determining the position without using ages. Because if you use ages and reconstruction, it's harder if you do that.
Yeah, great. And the last one, Daniele. Could you design a kind of elongation inclination correction with your Kiaman data? Because then you could apply it to all the sedimentary data, which is a lot of sedimentary data in Kiaman, and see what's the result. Is there any possibility of doing that, or do you think you have still too many variables there that I mean?
Well, my intention in this work was, I will find the same elongation for the Kiaman, and I will continue use the same procedure for correcting data because I don't want to measure anisotropy of remanence. This was my desire, but this doesn't happen, and we have a different shape. But also, we have an experimental error. So if you look at circular distribution, what do you remember? You remember from Fisherian distribution, that is error. So maybe we have a field that doesn't change. We are only looking to the experimental error, so we cannot use this for model. Mm. And the other thing that I saw using the best database that we have the last 5 million years, when you look to those data, you see that they are not totally in agreement with a mean field like a simplified GGP model. So I don't know if we can use this as we should try with the last 5 million years and see if we can really use as a prediction of what we should have in one place, in one sedimentary section. The thing is, for me, after these exercises that I did, trying to find a GGP model for Kiaman, or trying to see that the EI method works, the only thing that I think is that we should continue with the remanence, continue with the anisotropy of correction that we see, the anisotropy of magnetic grains, the anisotropy of remanence of the rock, so you are more near to the true flattening factor. So I would recommend this.
Yeah. Okay. Thank you very much, Daniele. Congratulations again, and also very nice presentation.
Thank you, Augusto.
Thank you, Augusto. It was a pleasure to have you in this committee. Now I ask Daniele to make his questions. So please, Daniele.
Can you hear me? Well, I'd like to thank you, Marcia and Daniele, as well for the invitation to participate in, as well as to greet fellow members of this committee. It's a great pleasure to participate of this defense. I know Daniele since her first academic steps, and I'm really happy because of that. Well, based on the reading of the thesis, it's pretty clear the originally relevance in trying to examine whether the GGP is valid to describe the Kiaman superchron. It's also possible to see that you really work hard in some aspects of modeling and carry out very interesting results on the extension of validity. And as a plus, you also obtain the reference PMAG pole, right, for Mafra formation. Well, I don't intend to go on for too long, especially after the important contributions, Dr. Constable, Dr. Rapalini, and I'm gonna try to be very objective in some specific questions. I make a list of a few remarks. Afterwards, I will convey to you and Marcia. And well, let's see. I try to talk about a few of it. Well, similarly to Rapalini, I mark it here exactly because of the complexity of working with late Paleozoic PMAG strategy. Why did you try also to investigate the PMAG data related to CNS, which is younger, with a better PMAG database, and also with more reliable paleointensity data? Well, you already discussed about that. I have a question about, did you also consider to test the GGP validity with older intervals that exhibit also a high geomagnetic reversal frequency? I mean, about in comparison to the last 5 million years. For example, the Illawarra hyperzone of mixed polarity.
No, I didn't did this.
No, I mean, if you intend to do it in the future.
Yeah, this is a good thing to do, and even for trying to, even we don't have the right prediction for a type that we should expect from the distribution, but for knowing the overall behavior of the past. So I would use for all older periods, or doing like a compilation from 2 billion years ago to evaluate how we can find other types of smoothed field, overall behavior of the field in the past. This is a good thing to do, good work to do, and I think it's a good idea. I would recommend this work to do, to see if we can measure this. Now in the reviewed papers that we take it back to JTI, we also included the correction of experimental error. So the work is better than this that we present in the thesis. So you can do this if you want, and you can use the code that's available. And this is a very nice idea. And this is, I think, a good idea.
Okay. A few more points in the text. I think the thesis is very well written. There are few, from my point of view, few mistakes. Just a few mistakes, and I'd like to point out something that I think it should enrich your text, especially in the introduction and in the theoretical background. In the chapter 1, page 19, don't you think it would be interesting to introduce what PSV is, as well as its cause? I think it's central in your work, and it could enrich your text. This is just my my impression.
Mm-hmm.
And especially, don't you think it would be interesting if you indicate why superchrons should be investigated, despite of the lower PMAG database in comparison to more recent times? Don't you think?
Lower?
I think in the introduction, it would be interesting if you explain why superchron is a target of yours.
Mm-hmm.
For example, a suggestion as a way to include it. All the main features of the geomagnetic field, reversal frequency, morphology, secular variation, and paleointensity might be better observed during superchrons, where geodynamics might be operating in its extreme. This is an explanation.
Mm-hmm.
And, well, so they are very special representatives of the geomagnetic conditions and can play a key role in providing new results and insights for testing different geodynamic models. I think a short paragraph mention it would be interesting in your text.
Mm-hmm.
I noticed that in some part of your text you use model G or G model.
Yeah.
I think you need to define one way or another for consistency. Model G, perhaps. Yes. Let me see a little bit more here. There's I think, I'm not sure whether I understood well. Also in introduction, in page 20, you wrote, because of the long duration of the superchrons, they are expected to have a more stable mean dipole field, and higher intensities than periods of high reversal frequency. Did you mean that superchrons are expected as exhibiting high intensities because of this long duration?
No.
I think there's a problem.
They are superchrons of a stable dipole.
Yes, but take a look on this paragraph afterwards.
Okay.
Okay. In the chapter in which you present the theoretical background of the thesis, you mentioned about odd and even families for describing the dipolar and quadrupolar families, as McFadden did. But don't you think that it's important to mention that they are respectively correspondent to the antisymmetric and symmetric harmonic terms around the equatorial region, as it reported nowadays?
Yeah, we can put also symmetric, or yeah, you're right, it's missing there.
And and about the model G, this is my feeling. I think it would be interesting to explain it as a phenomenological model, and that A and B are shape parameters, just for completude. Okay.
Mm-hmm.
At this point, and this is a question for you, why don't you include in your text that for obtaining angular dispersion data due to the TSV, it's important to be done this by minimization of sampling and measurements errors by means of that relationship, which includes the average number of samples per site and with inside dispersion. This is important, I think, as a theory. What's your opinion about this?
I think I put in the last chapter, in the chapter 5. It should be here, using the right correction in variation about the field, not that we have an experimental error here. Okay. Well, my last question for you.
You also said that the model G is based on a mathematical artifact. Could you explain it better to me?
Yeah, this is a work from Linda Gilder, and they discuss about when we transform from direction to VGPs, we have a nonlinear transformation, and then the distribution that we see in the VGPs are related more to artificial things. So if you have a distribution that is the same thing, like Fisheurian distribution at each place in the Earth, and when you transform this in VGP, because of this transformation, you have a latitudinal variation. So this is the work from the user, and so they say that this transformation it has, if you use the latitudinal variation, you can study mathematical artificial.
Daniele, sorry, I didn't get the last phrase. The signal was interrupted.
If you, according to this work, Linda Gilder, if you have the same distribution in all places in the Earth, when you transform this in VGP, you're going to have a latitudinal variation with the scatter. So right. They say that this is a mathematical artificial. Okay, if you work with this and you know about this, it is okay. It's only that it's about model G, it's about VGP dispersion. So I mentioned here in the past.
Okay, well.
The only problem of using the prediction from GGP model to VGP counter that I told is because when we look into the dispersion, we use Van Damme cutoff. And when we do this, we cannot predict anymore theoretically that dispersion. So you need to do simulation.
Okay, well, I think that's it. Thank you, Daniele. Again, thank you, Marcia.
Marcia, you are mute.
Marcia, you need to turn on your microphone.
I know, I knew that, but I was having a problem. Okay, thank you, Danielle. Now, Ricardo, please, your questions, and thank you for taking part of this committee. Please. Sorry.
Thank you very much, Marcia, and thank you, Danielle. And good afternoon to everybody. I'm really glad to be here, and I'm honored to be part of this committee. And I would like to congratulate Danielle and Marcia for their very nice work. Danielle, it's a very nice thesis. It's interesting because it's when I read it, I thought it was written like upside down, because it starts with the study case and then it goes more broad. But it's the way it's written is very easy to follow. It's because it's a kind of a chronological way, so you understand very much why you went to the models and why you needed those models you have built. And it's a big effort. I think it's a very remarkable work, and I'm very impressed, and I enjoy very much. I think that it's amazing also that it's something that you started to build in our group, and it's something really new, and you're bringing something completely new to the group you're part of, and it's very nice for us to have this. So let's. I just have some small questions, and I will not take this too long because it's the defenses in Brazil are very long usually. So I'd like just to make a first a comment. When you show your data in the magnetization data, you show that there is a systematic difference between AF demagnetized samples and thermal demagnetized samples, and you show that there is a systematic error or a systematic deviation in direction for those samples. This has an impact for your results, of course, as you show, but it makes very suspicious other results as well, because sometimes we don't have this comparison and people are not careful enough to do this. And for very old results that you have in your compilation, by the way, maybe this is also a problem. So when you do when you put error into your simulations, for example, you put the errors thinking they are not systematic. But those errors that you're describing in your work, they are systematic. So they deviate always along a great circle and to a given position. So this can have an impact of making the directions more shallow, or the declination higher along a great circle. And this will impact the delta E and the delta N, or both.
Mm-hmm.
So can you give me a way, or can you devise a way to think of how to reduce this kind of error in the database?
In the database?
Yes.
What I propose is consider the error from each site as a Fischerian error, and I use the projection of this error, the alpha 95, in the equal area projection. So they have the same size in east and north direction, and I corrected that. But for systematic errors, I'm not able to decide this, because I should know that the sequence has a systematic error that is different from each one of the directions. So I think it's not possible, I think.
Yeah. Would it be possible to think of modeling different errors along a great circle towards the present-day field, for example? If it was a Driscoll's secondary component, for example.
So I got like the secondary components of the work of the study that I am compiling and do an error that is elongated by the secondary direction, going to the secondary direction. Yeah, I think if I'm doing that, yeah, I think first I need to consider that the work has an experimental error that is not the experimental error that we are used to in sites. I cannot think about this now. I'm not able to think about this, but yeah, you can use different, if you have the direction of the secondary, you can compose and do a great circle, but I don't know how to do that and how to judge this, because I need to judge the study and say that
it's very hard, and I think that the other problem is that if you have an inclination error, is an inclination is an error that is along a direction or along a great circle. That is not necessarily the same error that's going to be this one that's related to a secondary component. So it means that in the whole database, you're going to have an error that is related to the dispersion, meaning the orientation error. Then an error related eventually to some secondary components that were not eliminated. And then for the sedimentary record, you're going to have an error related to the inclination.
Mm-hmm.
So this makes the testing of those ancient models very challenging in a way.
Mm-hmm.
So it's that's why I think that really having other information incorporated into the model would be very nice, because it's very hard to say that you're going to have a accurate model with all those problems.
Mm-hmm.
The second thing I'd like to address is the do you have any idea of what might be happening in the database for the Kiaman to have this 0 to 10 latitude window with such a difference in terms of variation in north south and east west, whereas all the rest has the same, more or less the same variation in terms of the direction of the magnetic components.
In terms of data, working with old data, we are looking to paleomagnetic poles. And the main intention of doing a paleomagnetic pole is finding a mean value. So when we do this, sometimes you don't have lots of samples per site, but that's okay because the experimental error will be removed together with the particular variation. So that's okay, and you find a final paleomagnetic pole and publish that data sheet. And when we look, and sometimes when you're analyzing data, you can think that some samples doesn't fit very well with the mean of the site, and you think, oh, this is maybe this sample has a weathering thing, and I will carve them. So the size of alpha 95 that we have in data sheets from paleomagnetic work, sometimes they are not corresponding to the real value. And also, if you have a small number of samples per site, you are pretty sure that you're not determining the real expected value of alpha 95. So you are not able to say that experimental error is well determined. So I think these things happen with the Kiaman database too much. We have old data. We have and I also did the exercise of taking because I took filtering process using only 5 sites per student studies per joined together. And when you do that, if you have only 5 sites and combine with other 5 sites, of course you're going to merge in a more grouped way because you have small clusters of data that you're putting together. But I was only able to try like a filtering process of n greater than 20 because we don't have too many data sheets with more than this. So one thing that maybe is happening here is that as we are taking small pieces of the digits of the PSV, and you're putting together at the same place, you're going to have a circular distribution. And maybe if you have a long series of data, you're going to determine well the declination of the expected direction, and you would fit well the data with the right elongation in the right position.
Okay.
I think the experimental error is inside this problem, and also the number of sites that we consider for doing this this exercise of joining data sets together. I think we have this problem.
Yeah, but in the case of the 0 to 10 window,
we have. I really don't know. I really don't know.
Yeah. Would you guess that eventually, because you have done that deliberately in the work, that you just eliminated this the 0 to 10 and trying to fit the model?
Mm-hmm. When we usually process more strict, these bands vanish.
Yes.
So I really don't know.
Yeah, because I know there is an old paper by Ade and Torsvik. I don't know if you know this one, 1996, in which they say, okay, you have in the Permian, you have such a very strange situation in which you have a supercontinent and a superchron at the same time. And eventually the superchron would be the result of a massive input of cold slabs into the core mantle boundary. So changing in a very significant way the core behaves, in fact, in terms of stability. So eventually, you're really dealing with an extreme case in which you have a very asymmetrical heat transfer behavior in the core between the core and the mantle. And also you have a very large lead of thick lithosphere at the surface. And as Augusto said, you're just sampling a part of this very asymmetrical behavior, asymmetrical condition of the Earth. That's why eventually you have a field behavior that cannot be completely modeled by a simple model. So eventually that can be a reason. But even though it's very hard to understand why you have this 0 to 10 band so different from the rest. So eventually this can be a problem of the data. The data is not good enough. And that's interesting because it shows that where we need to go. So we need to go to a place that were close to the equator in the Gondwana, and do a experimental work and see if it matches or not your model.
Mm-hmm. Yeah, we have the list of the sampling sites there in this database. Without working with a small number of sites, so we can go there and do more sampling. And what happened during that we have a superchron and we have two stable fields is Amici and Olsen, I forgot the name. They told that the superchron starts when the superplume vanish, it collapses. So then we don't have a plume heating process occurring in the mountain core boundary, and so when you have a superchron, you have not so much lateral difference, heterogeneous laterally in this mantle core boundary. So they explain this, the beginning of a superchron. And the end of the superchron starts a geomagnetic field more energetic with more reversals when we have a new superchron occurring nearby the mountain core boundary. But yeah, it's too strange, this band of data, and the thing is that it vanishes depending on the filtering process. And I think we have this database and we can explore more about sampling size, or maybe see the distribution, try a configuration approximately using Pangea reconstruction to see if you will see different things in terms of longitude. It should be a good test to do that.
Okay, for me it's more than satisfied. I'm very glad to be here, as I told, and congratulations for your work, and congratulations to Marcia. It's a very, very nice work, and for Katie also for her participation in it, and Danielle. I'm very, very happy with the thesis, and I'm sure you're ready to be a PhD.
Thank you.
Thank you.
Okay, so thank you, Ricardo, and thank you, all of you, for comments, questions, and ideas for future work and improvement of the present work. We now have to move to the discussion room to evaluate so the committee will decide what to do with Daniele. Daniele, I think you have to stay connected. So as soon as we finish, we go back to this room. All of you have the address, the link for the next.
Yeah, I have a question. It's just a matter of changing that set of letters in the browser. That's it.
Exactly.
Yes.
Just change that.
Okay. Okay, I'm going there.
Okay, here we are. No, I think maybe Catherine is having a problem. I will go back to the other room. No, I think looking for the.
Você ainda está na sala.
Márcia, você tem que sair dessa sala, porque você está aqui e fica gravando. E o Rapalini também tem que sair dessa sala.
Augusto, you need to go out of this room.
To get to another meeting.
Deixa eu ver o YouTube. Tá bombando, então? Deixa eu ver esse YouTube. Peraí, cadê? Como é que eu vejo isso? YouTube. Já achei. Ah, comentários, que legal. Tá gravando tudo. Ai, que legal. A Luciete. Tiago, Renato, Camila. Laura, minha irmã. Até a Papu. Ali, então. Oriana. Galera.
Tcharam.
Opa, voltaram. I was seeing the comments in the YouTube. I did a live. Ricardo, you're without your muted.
Okay, no, I'm not.
Wait Okay.
But Marcia is the one that is bringing the good or bad news. She's far from this room. So,
Mystery.
So are you still on YouTube, Danielle?
Huh? Oh, you saw. There are a lot of people.
Really?
Yeah, we are there.
Marcia, you need to turn on your mic.
Wow.
Okay, everybody's back.
Yeah.
So, Daniele, after this brief meeting and considerations, the committee wants to announce that we consider you approved and you are ready for your career as a doctor now. I think we can turn on the mics so we can clap for. Unfortunately, we can't hug you, but congratulations. It was a very good thesis.
Thank you for all of you that accept being here. This so important day for me. So I want to thank you guys and everybody that was with me along this trajectory. Thank you.
I think we can say for everybody, we are really proud of you.
Oh, thank you, Danny. Yeah.
Okay, so thank you very much for all of you, all the committee members, to take your time to analyze this work and give so special contributions. Hope to see you soon. And so we can end this session.
Okay. Can we take a picture of
I just took a picture for you, exactly when Marcia was telling you the news. Exactly in the moment.
Anyway, this will be recorded so we can go back to the session, okay? Okay, thank you very much.
Okay.
Bye-bye for all.
Bye-bye, Marcia.
Bye-bye.
Congratulations.
Thank you.
Congratulations, Dr. Brandt.
Ricardo.
Okay. Bye-bye.
Hope to see you soon in person.
Yes, and in another situation, please be safe. Take care.
Yeah.
Yeah.
Take care.
You too. Take care.
Goodbye.
Bye-bye.
Bye-bye.
Bye-bye.